All right, so this first one is just an invitation to apply some of your equivalences. You see we have an assumption is if P or R, then S or T, and you're supposed to derive from that not P and not R, or not, if it's not the case that S, then T. So if you want to prove to yourself that these equivalences are worth memorizing, then just try to do this one without them. In the past, you'd have to engage in some reasoning like, okay, this is a disjunction. Maybe I can prove one of the disjuncts first and then add in the other one for free. That's not going to work. And so in reality, what you'd end up having to do is derive some of these equivalences just to do the proof. Okay, but since we have the equivalences, what do you want to do? Well, just look at some of the relations here. We have P or R, which is related to not P and not R by De Morgan's. We have S or T, which is related to if not S, then T by material implication. And we also have the entire formula, which is a conditional, which is also related to the entire formula we're trying to derive by material implication. Okay, so it's totally up to you what you do, but since I'm doing this, what I think I'll do is see if I can convert not P and not R to P or R. So if you'll remember, or actually what I should have said is convert P or R to not P and not R. Now P or R is not in a negated form, but if you'll remember, we can change that by just introducing some negations with double negation. Right? So we can take advantage of our right to operate on parts of formulas using our double negation equivalence. So if I convert P or R to not P or R by double negation, remember it's very important that it's not negation elimination, because that was the original rule we were using, and it's a derived rule and would require you to be always operating on the main operator. So now I have the formula double negated, and of course now I can see that this part right here, right, corresponds to a negated disjunction, so I can apply to it this part of the formula, De Morgan's, right? Okay, so that gives me this. It's not the case that not P and not R by 2 in De Morgan's. And now suppose I decide I want to try to convert S or T, right, to if not S, then T. Well, here again, the form of material implication requires S, or the disjunction, to be a negation. So I'll just go ahead and convert it to a negation. Same basic step. So now I've got, it's not the case that not S or T, right? So now not S or T is the disjunction that's in the proper form. And so this is going to go to if not S, then T, right? Because the equivalent tells us that if A, then B is logically equivalent to not A or B, right? So here not S is our A, and not S is our not A. So this goes to if A, then B, which is if not S, then T. Okay, and so that gets us to here, and then we just need to figure out how to get the main operator to be a disjunction, and that's easy because this is a conditional of the form if A, right? it's not the case that not P and not R is our A, then B. So we can just apply material implication again quite straightforwardly and get not P and not R, or if not S then T, and then in one final step, double negation, or if you want to use good old negation. Nope, sorry, we can't use negation elimination because that's not the main operator, right? I bet you caught me there. But double negation allows us to remove the two negations, and we're like that. Okay, and that's number one. Okay, number two, the assumption is it's not the case that if P then S and R, so this is a negated conditional, which might get you thinking immediately about the negated conditional equivalence. And we're supposed to demonstrate a disjunction again. So to make short work of this proof, mainly what you want to do is notice that P seems to have been distributed into both disjuncts, and this is going to suggest to us that we might get some value out of the distribution rule. So what happens if we first negate the, apply negated conditional to 1, then we get P, and it's not the case that S and R, right? It's a straightforward application of negation conditional. So now you've got a conjunction, and really the natural thing to do here is just to break the conjunction apart, right? And that'll take you down a certain path. But if you've assimilated all these rules, and congratulations if you have, it takes a little while before they become intuitive. But if you've assimilated all the rules, you might notice that the disjunction we're trying to has P distributed into it, with S and R being the other two conjuncts in the subformulas. So this could indicate to you the possibility of distribution, by which I mean the distribution equivalence. Now, it's not in one step, but if you were to apply De Morgan's to not S and R, what would you get? Well, you get P and not S or not R by 2 and De Morgan's. And so that formula has exactly the form you need to apply the distribution rule, right? So this goes to P and not S, or P and not R. Essentially what happens is that the conjunction, right, becomes the operator in the subformulas, and the disjunction becomes the main operator, right? So there you have it, it's done. Now, you might be wondering, like, what happens, what would have happened if I had followed my regular intuitions? I won't do the whole proof for you here, but it is doable, and I'll just point you the way, and I'll put this proof up on the solution page in full. But essentially, you would have gotten to here, right? P by 3 and elimination, not S or not R by and elimination. And then you could just proceed by disjunction elimination, right? So you could build two conditionals. One would be if not S, then not this whole thing, right? And then if not R, then, excuse me, I think I said not. If not S, then this whole thing, and if not R, then this whole thing. In other words, get the conclusion twice from not S or not R. And it's actually really easy to do, right? Because you hypothesize not S, then you just add in your P through conjunction introduction, and then you can add in P and not R through disjunction introduction, and there you have it. Same thing works for R, for not R. All right, so I'll post that solution as well. All right, so number 3 gives us 2 assumptions to work with, not M and K. And if it's not the case that if K then M, then if it's not the case that P then Q. If it's not the case that if K then M, then if not P then Q. And we're supposed to we're supposed to prove if not Q then P. Now the rule I've taught you a while back was, if you're proving a conditional, then hypothesize the antecedent. That will totally work here. It'll always work. It's a good way to proceed. I would still just do it this way because it's just simpler bookkeeping. But I'll show you the way to do it without doing it that way, just to get some value out of our new rules. So you might notice that it's not the case that if K then M. If you apply a negated conditional to that, you're going to get K and not M, which of course is just a rearranged form of not M and K. So you can apply negated conditional followed by commutation, right, to get the antecedent of this conditional. All right, so then we get to apply our old friend conditionally, which gives us if not P then Q. And that's just how many steps away from what we want, right? Now make sure you apply the rule. Remember, my main warning here has been about negation management. So when you apply the rule, and the rule is going to be transposition now, what are you going to end up with, right? So it's going to be if not Q, then not P, right? Because not P is your A, Q is your B. So this goes to not Q, and if not Q, then not P. And then you can just apply your double negation rule. And Bob's your uncle. Now you can see what would have happened if you had started by hypothesizing not Q. Well, then you would have just derived not P, closed it off, and converted not P to P, or alternatively derived not P, converted not P to P, and then closed it off. Works either way. All right, number 4 is our first opportunity to prove a theorem. Now, a theorem is essentially the counterpart of a necessary truth, right? A necessary truth in the semantics is one that is true under all possible interpretations, also called a tautology, also called a validity. Validity, tautology, and necessary truth all mean the same things. In the proof system, which is where we're working now, a validity is expected to turn out to be a theorem. And so what a theorem is essentially an argument with no assumptions. So that means if it's a valid argument, it means that it can be derived from no assumptions. So since you have no assumptions here, you could proceed in one of two ways, right? One would be conditional introduction. One would be just to negate the whole thing and use negation introduction. Now you got so many rules now, there's so many sort of ways out where in the previous material you would have just got yourself hemmed in. You could actually negate this whole thing, apply the parentheses, and you'd have a negated conditional. Right? And then you could apply the rule of negated conditional and start looking for a contradiction. And ultimately, you would absolutely have to find one, or this would not be a valid argument. remember from the truth tree method, if you negate something that's supposed to be a tautology, it turns it into a contradiction. So the same thing would be expected to happen here. But let's not do that. And I'm not discouraging you from doing that. We just can't explore every possible way. Let's stay with sort of the routine I've given you, which is when you do have the main operator as a condition, then hypothesize the antecedent, right? And derive the consequent. But here you notice that the consequent is also a conditional, right? So this is your H1, your first hypothesis. Not M will be your H2. And then what you need to do is derive not S or not Q. Now, what I'd like to point out to you here is this is a disjunction, right? And you know that a disjunction is just a conditional by another name. And now you have material implication equivalence to take some advantage of that, right? So if you think about not S or not Q, you know that's equivalent to if S, then not Q, right? By material implication. So since this is effectively a conditional, you could also hypothesize S. And that just means that all you're after is not Q. Now, you don't have to do it that way, but this is available to you. And it's a good, solid way to approach things. And it's a nice little wrinkle, a new little technique that you should put in your pocket. So what happens if we do that, right? We hypothesize if S, then if Q, then M. Then we hypothesize not M. Then we hypothesize S. Now all we want is not, well, pretty clearly, S will give us if Q, then M, and then not M applied to if Q, then M through modus tollens is going to give us not Q, and that's it, right? So two simple little steps, and then we just get a bunch of hypotheses to discharge, right? So if Q, then M by conditional elimination, not Q by 2 for modus tollens, right? Now we discharge all these hypotheses. So, of course, as we said, the first one is going to be if S, then not Q, and that's not what we want. What we want is not S or not Q, but that is something that you can do it later too. But let's go ahead and take care of it now since it's on our mind. So that goes to not S or not Q. By material implication, and then we have if not M, then not S or not Q. So drop a line there. Right? If not M, then not S or not Q. And then finally, we have the entire formula. Again, by conditional introduction, but now it's 1 through 8. Okay, so a nice little combination of a derived rule and equivalence, your old friend conditional introduction, and a nice little wrinkle on that as well. Okay, number 5 is another theorem. It also happens to be a formula where the main operator is a conditional. Now the consequent is not a disjunction, but a negated disjunction. So we're not going to be able to use the same expedient that we used last time by hypothesizing again, but let's get the first hypothesis out of the way. Okay, so I didn't emphasize this before, but make sure, right, that when you hypothesize on the very first line that you indent, right? That's essential to the method of hypothesis. Feels a little weird to be indenting on the first line, but that's how it works. Okay, so from this conjunction, we are being asked to derive it's not the case that not P or not R. So you could just continue to work on the conjunction in its current form and do some substitutions with your equivalences, but that doesn't seem like it's going to be that productive given this is what we're looking for. So maybe just go ahead and break those down, break the conjunction down right away. So you've got, it's not the case that if P, then not P, and it's not the case that if R, then not R. So hopefully you see these are both negated conditionals. So you could apply negated condition to both of them. Get P and not P, and R and not R. Well, this is a conjunction of, both of these are conjunctions of logically equivalent expressions. They're just redundant, but clearly you can get P and you can get R. And so you can have P and R, and then the question would just be whether you can convert it to this. And maybe you can see right away that the answer is yes by applying De Morgan along with some double negation. So we've done exactly this before, and so you should definitely be doing this on your own now. So what I've done is rather than take P and R, P and R, I've taken not P and not R because that's actually what I'm looking for to perform my ultimate conversion. Right, so I get not P and not R, and that is equivalent, right, to it's not the case that not P or not R by De Morgan. And that's all there is to it, except for discharging our hypothesis. Right, so 1 through 9, conditional introduction, and that's the whole deal. All right, yet another theorem, and yet another theorem in a conditional form, and as you can see, it's nested conditionals. Okay, so go ahead and set that up the way you know how. And you get this, right? Hypothesize Q or not T, hypothesize T and S, and now all we have to do is derive Q or L. Well, this is a cinch, right? Because what we need is to get T on a line by itself. T, right, is equivalent to not T, which is the negation of not T. So here again is a question you should be able to answer. Would it just be okay to get T on line 3? Right, here's the question. Write 3. So 3 T, right? By 2 and elimination, and then on line 4 we get Q by 1, 3 disjunctive syllogism. Now the question is that okay? And the answer is no. Why not? Because T is not the negation of not T, right? So this actually has to be not T. So you just have to apply the double negation rule first before you do this. Again, in a way, one of the main themes of this homework review is negation management. So you can have T by conjunction elimination, might as well get S by conjunction elimination. Turns out here you don't need it, so this is kind of a wasted step, but there's no harm in doing that if you haven't completely strategized a result. This is just something you can do. So then we go to not T, right? That should be more like that. right? So not T, and not T will give us Q as we by 1, 5, right? 1, 5 disjunctive syllogism. And then this is just old hat now. You've got disjunction introduction, and then you're discharging both hypotheses. So disjunction introduction, Q or L on line 6, right? And then we've got what we want. We've got Q or L, so discharge the hypotheses, and you are there. So first one, if T and S, then Q or L by conditional introduction. Second one, the entire formula by 1 through 8, conditional introduction. Okay, so this isn't quite halfway through the homework, but it should be close enough to give you a running start on the rest of it.